All right, today we're going to take a tour through C++, which is, one of the most powerful and influential programming languages ever. We're not just going to look at code, though. We're going to dig into its core philosophy, how it lets us build these massive, complex digital worlds starting from the simplest possible ideas. So, let's just dive right in. This quote from Blaise Pascal, it absolutely nails the spirit of what we're talking about today. It perfectly captures the essence of great design, and especially C++. See, great design isn't just about piling on features. It's about the exact opposite. It's about distilling an idea down to its simplest, most elegant, and most powerful form. And that's really the philosophy we're going to unpack here.
So this really brings us to the fundamental question, right? The core challenge of all programming. How do you tell a machine, a thing that only gets super simple rules, basically just ones and zeros, to build something incredibly complex, like a Mars rover or a video game? Well, C++ has a very specific answer to this, and it all starts with the absolute basics, the raw materials of the digital world.
Okay, so let's talk about those basic building blocks. Every great structure, whether it's a house or a piece of software, starts with its raw materials. And in C++, these are the fundamental pieces. You can think of them like digital bricks and mortar that are going to form the foundation for everything else we build.
I mean, look at how simple these really are. You've got your bool, which is just a simple on-off switch, true or false. Then there's char for a single letter or a symbol. You've got int for whole numbers, 42, minus 273, whatever. And double for anything with a decimal point, like pi. That's it. These are the absolute rock-bottom fundamental units the computer gets. Everything, and I mean everything, is built up from these.
Okay, so we have our pile of digital bricks. But a pile of bricks isn't a house, right? You can't build a skyscraper with just a pile of bricks. You need to start putting them together to make walls, floors, entire rooms. And it's the exact same idea in code. We have to combine these simple types to represent our much more complex ideas, like, say, a 3D model or a video player.
And this is where the real magic of C++ starts to show. See, instead of just giving you a giant box of pre-built, one-size-fits-all tools, C++ does something much more powerful. It gives you the ability to create your own tools, to forge your own custom blueprints perfectly suited for whatever job you're trying to do.
So our first attempt at a blueprint is something called a struct. Honestly, the best way to think of a struct is like an open box of parts. You just throw related things in there. So for our vector, which is really just a fancy list of numbers, we'll toss in the size of the list and a pointer, which is basically just the address for where the actual numbers are stored. It works for grouping stuff, but it's a little too simple. It's just an open box. Anyone can reach in and fiddle with the parts, and that can lead to a lot of problems.
So that open box idea leads us to a much, much better blueprint, the class. Now, what a class does is it takes that open box of parts and it snaps a protective case around it. All the messy, complicated internal workings, they're now private. They're hidden. The person using the tool can't mess with them. All they get is a clean, public interface with a few simple buttons and controls, like a function to get the size. Suddenly, it's not a box of parts anymore. It's a finished, reliable tool.
And that's really what a class is. It's our master blueprint. It doesn't just list the parts, it also defines how the whole thing works. It bundles the data and the operations together into one single, neat package. And once you have this blueprint, you can crank out as many identical, perfect copies of that tool as you need. This idea, this bundling of data and function, it's a cornerstone of pretty much all modern programming.
Okay, great. So now we can create our own custom tools and blueprints. But what happens when your project gets huge? We're not just talking about one workshop with a few tools. We're talking about a massive factory floor with thousands of different blueprints. How in the world do you keep all of that organized without everything just descending into total chaos?
Well, the solution is to think like a modern assembly line. You separate the what from the how. First, you have the public blueprint. This is often in a file ending in .h. This is the design spec that everyone gets to see. It tells you what the tool does. Then you have the factory, the .cpp file. This is the private assembly line where the tool is actually built. All the messy details are hidden in here. And finally, you have the customer, or the user. They only need to see the public blueprint to use the tool. They don't need to know or care how the factory puts it together. This separation is absolutely crucial for managing big projects.
And, as our factory gets even bigger, we need another layer of organization. That's where namespaces come in. Just think of them as different departments in the factory. You've got the STED department, which stands for standard, and they make all the common everyday tools everyone needs. Then you might have your own department making specialized tools. The reason this is so important is it prevents confusion. So if the plumbing department has a tool called wrench, and the engine department also has a tool called wrench, the namespace keeps them from getting mixed up.
All right, so we've covered how to build individual tools and even how to organize a whole factory of them. Now we get to move up to the highest level of design, modeling really complex ideas. This is where C++ lets us represent not just tangible things, but abstract concepts, and, crucially, the relationships between those concepts.
Think about how we talk about the world. We understand these relationships intuitively, right? A circle is a kind of shape. A poodle is a kind of dog. We get that. But how do you actually represent that is a kind of relationship in your code? That's the next big puzzle to solve. The way we do it is we start with a purely abstract idea. We create a class called shape. Now, this isn't a circle or a square. You can't actually make one of these. It's more like a contract or a promise. It says, hey, if you want to call yourself a shape in my program, you absolutely must know how to do these things. You have to be able to be drawn, moved, and rotated. It defines what all shapes can do, without saying anything about how a specific one does it.
Okay, now that we have that abstract contract, we can start getting specific. We can create a new class and declare that a circle is a kind of shape. Because of that, it automatically inherits that contract. It promises it knows how to be drawn and moved. But then it adds its own unique details, the things that make it a circle, like a center point and a radius. We've just taken that abstract idea of a shape and made it concrete.
And we can just keep layering these ideas on top of each other. Why stop there? A smiley face. Well, that's really just a special kind of circle, right? So it inherits everything a circle is and can do, but then it adds its own unique parts, like eyes and a mouth, which, if you think about it, are probably just more shapes themselves. You see how we're building up this really complex object out of simpler, related ideas? This whole process, from hiding the guts of a tool inside a class, all the way up to defining what a shape is, it's all driven by one single, incredibly powerful concept: abstraction. It's the principle of focusing only on the essential ideas while hiding all the messy, complicated details. C++ lets us build these layers of abstraction, moving from raw materials all the way up to entire finished systems, and it's how we manage to build things that would otherwise be way too complex to even think about.
And so that brings us back to our very first question. How do you tell a simple machine to build a complex world? Well, this is C++'s answer. You start with simple rules, the simplest building blocks, and then you provide the power tools to combine them, to organize them, and to model them into layers and layers of abstraction until you have built an entire digital world.
And believe me, this is not just some abstract theory. This philosophy, building huge, complex systems out of small, simple, reliable components, it's the engine running behind literally billions of devices you see every day. We're talking about everything from the Mars rovers exploring another planet to the operating system running on the phone that's probably in your pocket right now. These principles are at the very heart of so much of the technology that powers our world.
So, I want to leave you with this final thought. This way of thinking, in terms of blueprints, interfaces, and abstractions, it's not just for programmers. It's a really powerful mental model for understanding any complex system. So, take a look around you. If you could design a new blueprint for anything in your world, what would it be? What would you build? Thanks for joining me on this tour.